Hello everyone, I'm Calvin Joseph and I'm a PhD student at IIT Kharagpur, and today I'm going to teach about the series RLC system regarding its transient and frequency response. So today I'll be teaching about the series RLC, and the circuit will look like this. There is a resistor R that has an inductor L, and there's a capacitor C. Okay, and over here is the input is applied, and over here the output is seen. So we are seeing the output across the capacitor, the voltage across the capacitor, and input we can apply anything. Either we can apply a square wave or a sine wave, which we will see one by one. So let us analyze the circuit. When we convert it into Laplace domain, this will become R SL 1 by SC. And over here, whatever is the voltage, there's a V in of S. And over here, it is the output of S. So when we derive the transfer function, we will get it as V output of S upon V in of S based on the potential divider rule. It become 1 upon SC divided by R plus SL plus 1 upon SC. So when you put the 1 upon SC in the denominator, it becomes 1 upon S square LC plus RSC plus 1. So it is desirable that the highest order of S will have be unity. Okay, so what we do is we divide throughout by 1 by LC. So it becomes 1 upon LC square plus R S by L plus 1 upon LC. So this is the transfer function for the series RLC system. So let us denote it as G of S. Okay. Now this is a second order system, and a generalized transfer function for a second order system is given by omega n square s square plus 2 zeta omega n s plus omega n square. So now when we compare, what do we get? Omega n is equal to 1 by root L C, and 2 into zeta omega n is equal to R by L. When we do substitute value of omega n, what we get is zeta is equal to R by 2 root C by L. So now omega n is known as the natural frequency. This is the natural frequency of the system. And zeta is known as the damping, which is present in the system. So there are three cases. If zeta is between 0 and 1, the system is known to be underdamped. If zeta is equal to 1, then it is critically damped. And if zeta is greater than 1, then it is known to be overdamped. Right? So how do we know what is the damping of the system? When we will apply, let us say, to the input, I will apply what is known as a step. It goes from 0 to 1. So this is my input. Then how will my output respond? That curve, we will see. So the output can respond like this. It can oscillate and finally settle at this. Or another case is it can go like this and reach. Another case is in which it will take a lot of time. So this is the curve for the underdamped case. This is the curve for the critically damped case, and this is the curve for the overdamped case. So this is how the transient response will look depending upon your damping. Okay, there are various other criteria are there. So this is known as your overshoot. Okay, your overshoot. Go to the next page. This is known as your overshoot. The time it takes to reach the maximum is known as your peak time, as well as the time when it takes to reach within 2% of the steady state value. That time is known as your settling time. Okay, so these are certain parameters which we use to uh, to to describe about the transient response of the second order system. And now we will see what is the formulas given for these. Okay, so my peak time is given by the formula pi by omega n square root of 1 minus zeta square. My settling time is given by the formula 4 by zeta omega n. And my overshoot is this. Okay, this is my overshoot. So my overshoot, and this is the final steady state value. So the percentage overshoot is given by overshoot minus steady state upon steady state into 100. This is my percentage overshoot. And the formula for the percentage overshoot is given by E minus zeta pi by square root of 1 minus zeta square into 100. Okay, so this is the formula for the percentage of overshoot. So now we will consider a case, which we will also do some LTSpice demonstration to show how we will look into a circuit. Okay, so let me open the LTSpice simulation. Okay, so this is the transient response for a this is the series RLC circuit, which is over here. So we have a resistor of 600 ohm, an inductor of 100 millihenry, so just 0.1 Henry, and capacitance of 0.1 microfarad. Okay, so now let me run the response. So this is how my input is changing. My input is changing from 0 to 1 and back to 1 to 0. And this is how my output is changing. So you can clearly see that it is underdamped. Let us see a case when it is critically damped. When it is critically damped, you will see that there is no overshoot. It is just reaching the final value. It is going from 0 to 1. Okay, it is going from 0 to 1, but there's no overshoot is present in this response. Let me make it overdamped. You will see it is taking a bit more time. It is taking a little bit more time. Let me do a case where it is more clear and easier for you guys to see the difference in the response. So put a sweep on. So we will consider three cases. So I have given a command which basically will get 1000 ohm is for an underdamped case, and then 2000 is for critically damped case, and 3000 is for the overdamped case. So let me run the response. There was a mistake. It only ran for one case. So first is for 1000 ohm, then is for 2000 ohm, and then is for 3000 ohm. Okay. So the green one is the underdamped case, the blue one is the critically damped case, and the red one is the overdamped case. So how changing the value of R? When I change the value of R, these cases were occurring. So let us go back to this one. So what is my L? My L is 0.1 Henry and my C is 0.1 microfarad. So my omega n, which is equal to 1 by root LC, is given by 1 upon square root of 0.1 into 0.1 into 10 to the power minus 6. So my omega n is actually equal to 1 upon square root of 10 to the power minus 8, that is 10 to the power 4 radians per second. Okay, this is the omega n I got. Now, main case is my damping I want to know. So what are? So my damping is given by R by 2 root C by L. So this is equal to R by 2. C is 0.1 into 10 to the power minus 6. L is 0.1. So my damping is given by R upon 2 into 1 upon 1000. Okay. So my R is 2000 into the damping. So I consider three cases. My damping was 0.5, 1, and 1.5. So my R in this case will be 1000 ohm, which we used, then 2000 ohm, and then this case will be 3000 ohm. So this is the underdamped case, this is the critically damped case, and this is the overdamped case. Okay, so that is why I chose these values of resistors, right? Now, we will consider a case when the damping is zero point 0.3. Okay, when the damping is zero point 0.3, my R should be 600 ohm. And we will see what will be the overshoot, etc. We will look into it. So let us first do some calculations. What will be my settling time? My settling time is given by 4 by zeta omega n. This is 4.3 into omega n is 10 to the power 4. So let me use the calculator. So this comes out to 1.333 millisecond. My peak time is given by pi by omega n square to 1 minus zeta square. So this comes out to be this comes out to be 0.329 millisecond. And my overshoot, percentage overshoot, is given by e to the power minus zeta pi square to 1 minus zeta square into 100. So that comes out to be 37.23%. Okay. So now let us simulate this and check whether we are getting the same response. So what I want my R should be actually 600. Okay, and these steps I don't want them. So I'll comment them out. My R is 600 ohm and let me run the response. So this is the response I am getting out the output. Okay, there's a steps into 0 to 1 and then again going to 0, and this is how my output is changing. So let me see what is the peak value. Like peak value, how much time it is taking. So to do that, let me add a cursor. So this is the initial time Okay, let me add one more cursor. So there are two cursors. So cursor 2, I will take it to this point. When it reaches the maximum, I think better if I zoom in also. So cursor 2, I'm taking it at the maximum point, and cursor 1 is from the time of the step. So you can see that the time it is taking is 320.2864 microsecond. This is the peak time. And according to our calculation, we got it to be 0.329 millisecond. So 0.329 millisecond can be written as 329 microsecond. So it is closely matching. Okay. And now, what is my steady state value is 1 volt. Right. So my peak value will be equal to steady state plus my MP. Okay. So this is equal to 1 plus 37.23 divided by 100. So my peak value is given by 1.3723 volt. And if you see over here, the peak value is cursor 2 is coming out to be 1.336 volt. If you see, it is 1.371 volt. So it is very closely matching what we have done analytically. Okay. So this is how we can see that it is matching with our theoretical formulas. Let me show a case about how in underdamped for different values of zeta, how does it change? Okay. So this is when the zeta is 0.1, damping is 0.1. Then when damping is 0.2, then damping of 0.3, damping of 0.4, how is the curve? Then again damping of 0.5, and damping of 0.6, and damping of 0.8. So you can see as you increase the damping, it is the overshoots, all that are less. Let me zoom over here. So these are for different damping ratios. Okay, this for the underdamped case alone. So as the damping is poor, the overshoots are more, but when the damping is more, the overshoots are less. Okay, so depending upon our requirements, we can decide what damping is required. So this concludes the transient response to the series RLC. Now I'll proceed with the frequency response. We'll start with the frequency response. We have a resistor, an inductor, or capacitor. Okay, these are L and C. What happens in frequency responses? We apply a sine wave. We will apply a sine wave, and since this is a linear circuit, it is a linear circuit. At the output also there will be a sine wave. So we apply a sine wave input. Output also will be a sine wave. Okay. So if this is my input sine wave, my output sine wave will be something similar. Okay, it will have some lag and it will have some change. Okay, so let my input be equal to A into sine of omega t. My output will be equal to B into sine omega t plus 5. Okay, so it is at one particular frequency omega. At frequency omega, my gain is equal to B upon A. That is the amplitude. And the phase is equal to phi. Okay, this is the phase lag. Okay, it is minus phi. So this is the phase lag which is there at this frequency. Okay, what we do in the frequency response is we sweep the frequency. Means we change omega. Okay, we will keep changing omega. And we know that a transfer function of this system is given by omega n square s square plus 2 zeta omega n s plus omega n square. So it is a second order system. So the Bode plot of this system, if we draw it, it will be something like this. There will be some peaking and then it will fall. Okay, this is the gain curve. And the phase curve will start at 0 degree. It will go on, and at this point, it will reach around minus 90 degree. And finally, at steady state, it will settle at minus 180 degree. Okay. We have considered one particular situation where the natural frequency is 500 Hertz and the damping is around 0.3. Okay, these are some calculations which I have made prior to recording this video. So I will run this. So this is my input and this is my output. So both are here. Let me please. So both V output and V input both are in phase. Okay, both are in phase and both have equal amplitude. And this is at the frequency of 50 Hertz. When my frequency is much less than my natural frequency. Now I'll consider a case when my frequency is equal to the natural frequency. Okay. Let me run it. So now it's not looking good. Here, let me pause. So you can see my V output and V input are plotted together, and you can see there is a phase shift of minus 90 degree, and the output is more than my input. Okay, so there's a gain. So that gain is given by 1 by 2 zeta. Okay. Now let us consider a case when the frequency is 10 times of the natural frequency. Let me run the analysis. So now you can see that the output is very small as compared to the input. And in this case, let me use another plane. So if you see, you zoom in, when your output is maximum, your input is minimum. Okay, so that is like 180-degree phase shifted, and the attenuation is very high. Okay, at this high gains. So using this information, we will get the gain and we will get the phase, and we will then draw what is known as a Bode plot. So that Bode plot can be drawn using this LTSpice. Okay, so there's a command which will draw the Bode plot of it. So now we will draw the Bode plot. So this is how the Bode plot will look. Okay, where there is an gain is present. And there's a gain plot and this is the phase plot. So let us go back over here and let me do some further calculations. So in this case, my L is 0.1 Henry, my C is 1 microfarad, and my frequency omega n is 2 pi into 500 radians per second. My R is 190 ohm My damping is around 0.3. Okay, this is what we know. So we know that the Bode plot will come like this. Okay, so this is the Bode plot way it comes. And you can see that there is a peak. The peak is present. So how the formula for that peak is given by 1 by 2 zeta square root of 1 minus zeta square. And this occurs at the frequency of the peak is the natural frequency square root of 1 minus 2 zeta square. Let us do the calculations. So this peak is given by 1 by 2 zeta into square root of 1 minus zeta square. So this is actually equal to 1.7471, and this peak is given by 500 square to 1 minus 2 to 0.3 square. So this is 452 hertz. Okay, this a better way, because in the Bode plot is showing in dB, we do 20 log the base 10, 1.7471. So this is equal to 4.846 dB. Okay, so now let us check whether this is matching with our simulation. So let us zoom in and let me take a cursor. So if you see in steady state, the gain is 0 dB. Okay, it is 0 dB in steady state. Now let us go to the peak point. So this is the peak point. Here, the magnitude is 4.83 dB and the frequency is 456.6 hertz. So it is very well closing to, it's very well matching what we got over here. Okay. Now, let me consider a case where the damping is changing. Okay, and we will see how, as the damping changes, how the response will look. If you see over here, if you see this curve, this is how the damping starts from 0.1, it's going all the way to 0.1. It's going to 1. Okay, 1, 2, 3, 4. It is going like that. Okay, so there is always that peak is happening. A peak is happening, but as my damping constant becomes more and more, this peak is reducing, and afterwards it disappears. There's no more peaking effect occurring. But you can see that the phase is becoming minus 90 degree at this point. At this point, which is 500 hertz, my phase is always becoming minus 90 degree. And when the frequency is becoming very high, it is tending to minus 180 degree. And initially, the frequency is 0 degree. Okay. The initial amplitude is 0 dB. This is the low frequency asymptote. And then this peaking is occurring. And then from here onwards, it will decay at a rate of minus 40 dB per decade. Okay. So I hope you enjoyed this video and thank you for your kind attention. If you have any doubts and any queries, kindly post it on the comment section. Thank you.